Great. So good afternoon, everybody. Indeed, welcome to this experimental part of the session. First off, thank you to the organizers for this beautiful, beautiful workshop on my absolute favorite topic. So my last slide gave it away, but you might wonder, where is Washington University? If you've already forgotten what was on the previous slide. Because you might think that Washington University is in Washington State, in Seattle. That would be a reasonable guess, but it's not. You might think that it's in Washington, D.C., the other side of the country, but it's not. It happens to be in St. Louis, Missouri. And I have an experimental research group there in Washington University where we work with superconducting qubits. So thanks to Benjamin for giving a very beautiful lecture yesterday about all of the intricacies of superconducting qubits and how they work. I think of all the research groups, we aspire to be the most like his group, and so the techniques are very similar, and so forth and so on. So you have a good background for what we do. We focus generally on open quantum systems, so various questions in that domain, so things like non-Hermitian dynamics, I'll tell you about that today, but also dissipation engineering, Zeno effects, entanglement, metrology, quantum thermodynamics, new types of qubits, lots of fun things to do. But I'll try to keep it focused on one concrete story today. Before I do that, let me acknowledge my research group. Here's a picture of us last year, and in particular the students who've contributed a lot of the research to this and many wonderful collaborators over the years. So the trajectory of today's talk is as follows. I'm going to start with a discussion of monitoring spontaneous emission of atoms, very much along the lines of Klaus and Howard's beautiful lectures earlier this week. So talking about quantum jumps and diffusion, etc. But then I'm going to ask the question, what about the case where there's no quantum jumps? This is a case where one can then describe the evolution with an effective non-Hermitian Hamiltonian. I'll take you deep inside the sort of intricacies of that world about Riemann sheet topologies, adiabatic evolution in that landscape, and all the cool things that happen before quantum jumps occur. So, and then at the end, I'll tell you about some of our efforts to really make that world a reality with maybe some implications for quantum technologies. Okay, so rewind to Monday's lecture. Klaus was telling us about quantum jumps and what happens when you monitor the spontaneous emission of an atom with a photon detector. So picking up after his discussion with my own sort of simplified picture of it, let's revisit the story of the spontaneous emission of an atom decaying under radiative decay. So here's my drawing of an atom, if you like, or it's, in our case, it will be a superconducting circuit, an artificial atom. It's in its excited state, and we imagine it could decay to its ground state via spontaneous emission. And we imagine detecting that emission with a photon detector. So the story is quite simple. The atom starts in the excited state, the detector is waiting for a click, okay? And so that continues along until, at some point, we get a click. That clicking of the photodetector causes a quantum jump in our state for this quantum system. Okay, so there's a quantum jump to the ground state, and now the atom's in the ground state and the story is over. Quite simple. The point here is that there's a particular correlation between the state we have for an atom and the signal that we detect. Now you could ask, what if we measure that spontaneous emission in a different way? And this is something Howard talked about beautifully this morning, giving away some of my surprise, perhaps, that's okay. That is, light has both a wave and particle nature. So the particle nature pertains to photon detection, and the wave nature pertains to, say, does the wave interfere constructively or destructively with some other wave, a local oscillator? And there's two ways in which we measure the wave nature of light. It's homodyne detection and heterodyne detection. So, for example, here's a drawing of a homodyne detection. The atom can decay via spontaneous emission. That light is channeled into a homodyne detector. In our case, this is a phase-preserving parametric amplifier. Long story short, it performs homodyne detection of that field. I'll also mention that we were very much inspired by Benjamin's beautiful work performing heterodyne detection of spontaneous emission. And so we set out to construct a similar apparatus with the kind of amplifiers we have that perform homodyne detection. Okay, so we set up this system, and this is the first piece of data that I'll show you, and record the homodyne signal from an atom undergoing spontaneous emission into a single mode of the electromagnetic field, which we capture with this detector. And so you can see the measurement signal there is first off very different than the type of detection we get from a photon detector, which would be silence, 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 click, silence. Instead, it's a bunch of noise, and of course this comes from the vacuum noise, which we're measuring in one of those quadrature bases, the I or Q quadrature, or X or P, depending on how you like to define it. So since our measurement signal is so different, what's the new correspondence between the state for our atom and the signal that we detected? Okay, well, we can get into this because we're quantum trajectory people at this conference. And so what we're going to do is we'll write down for each of these detection events. So we've digitized our signal according to some bandwidth. And so in time, we have many different measurement results. In each of these measurement signals, we can associate with a measurement operator. And we can use those measurement operators to create a piecewise continuous quantum trajectory for our state. We might represent it with a density operator rho. And for convenience, I might plot for you the expectation values of the Pauli operators, sigma x, sigma y, and sigma z. The physics behind the measurement, of course, is that we're detecting something that's proportional to sigma minus, because the interaction with the field, the atom in the field, is a dagger sigma minus. And when we're doing homodyne measurement, we measure one particular quadrature, which ends up being like the real part of sigma minus. And that's going to be proportional to sigma x of the atom. So our signal is proportional to sigma x plus noise. Okay, so here's a drawing of one plane of the Bloch sphere. I've oriented it so that the excited state's at the top of the Bloch sphere for some sort of intuitive reference. And we'll plot the quantum trajectories of this signal system. So the first thing we could do is we could look at, for example, the first measurement signal. You can see it's negative. And so since the signal is proportional to sigma x plus noise, that negative value means that there's some back action that pushes the qubit toward negative sigma x. It's a weak measurement because it's masked by noise, and so there's a small change in the signal, bringing it to right here. I feel like it's a little loud, sorry. Great. Can you still hear me okay? Great. Okay, but then if you look at the next few measurement signals, this one, this one, this one, they're all positive values, and those correspond to back action, which are going to cause the qubit to actually go back over the top of the Bloch sphere, heading toward the positive x-axis. Okay? So the story of spontaneous emission unfolds in a sort of diffusive motion around the Bloch sphere, eventually finding its way to the ground state down at the bottom. Now in practice, because we're experimentalists, we don't do a perfect job of things, and we actually detect only a fraction, about a third, of the emitted light from this atom. That means we have to average over all those undetected photons or undetected homodyne signals, and so we end up with a mixed state representation of the quantum trajectory. It looks somewhat similar, but it's now within the interior of the Bloch sphere because we have to average over the missing information. But again, it diffuses now through the interior of the Bloch sphere from the excited state to the ground state. Each time we do the measurement, we get a different stochastic trajectory, and we'll get a different quantum, different signal and a different stochastic trajectory. Okay, so the picture here I'm contrasting is that of quantum jumps when we make photon detection. So here's three different quantum trajectories we might have. If we detect a photon here, we do it again, maybe we detect a photon here, etc. So we have these three different quantum jumps, and you could imagine performing experiments on an ensemble of such decaying systems and looking at the average evolution of these quantum jumps, which would, of course, recover this familiar exponential decay. But in the case of homodyne monitoring or heterodyne monitoring, we have this quantum diffusion, this diffusive evolution, in which case the trajectories are not abrupt jumps to the ground state, but they instead diffuse their way down to the ground state. And there's all sorts of peculiar things that happen in there. For example, here it's decaying, but at some point it's actually becoming more excited while it decays. And I know Klaus has a nice paper on that. Fortunately, though, if we average all these diffusive trajectories, we recover the same ensemble evolution, the same exponential decay. And that's encouraging, because if we hadn't looked at the light emitted at all, we'd hope we'd get the same response. Okay, so these are two unravelings, as we've talked about already today, of the Lindblad master equation, which I've written here. And what we do when we're looking at these quantum trajectories is we're updating this to be a stochastic master equation. So just as Pierre and Howard showed earlier today, you can write down a beautiful set of terms that go over here that add on to the master equation description and update from the measurement that we've received. And it's beautiful because it works in the case where we have a finite detection efficiency. So I refer you to the morning talks to understand all the beauty in this blue box right here. This discussion, though, now gives me a chance to tell you about non-Hermitian dynamics that are happening, sort of hiding in plain sight for this Lindblad master equation. Okay, there's three terms. There's this sort of unitary term corresponding to some Hamiltonian driving on the system. There's a jump term, and the rest is like what we call a coherent non-unitary term. Of course, it's been known for a long time that if you somehow eliminate the quantum jump term, you can recast these other two terms here in terms of an effective Hamiltonian that is non-Hermitian. So this is the new generator of time translation for a system, and now we can describe the trajectories of pure states with the Hamiltonian description undergoing sort of radiative decay, but without those quantum jumps. So how would you do this experimentally? How would you realize the no-jump evolution? Well, you might imagine surrounding your atom with 4 pi steradians of detectors, photon detectors, and hoping that not in one of those clicks over some time interval. Question? Drop which term? This term? I'm not, potentially, I'm not quite sure. I haven't thought about it that way. So what do the trajectories look like without quantum jumps? Well, we can imagine writing down a set of Krauss operators corresponding to the two type of detections we might have. So one for the case where we get a click from any one of these detectors, that takes the excited state component of our state and projects it onto the ground state. And one for the no-click evolution, which is given here. So what happens if we have no clicks? Well, imagine we started off in a superposition of ground and excited states, and then we continue to detect no clicks over time. Well, we can imagine starting with the initial state and applying this no-click Krauss operator over and over and over again, building up the state at each moment in time. And you can see this no-click Krauss operator, it reduces the amplitude of the excited state. And so as we apply it over and over and over again and renormalize the state, we can see we're going to start with a state that has some amplitude for both ground and excited, but deterministically over time progress to something that looks like the ground state. So although it's in some sense a stochastic evolution, we're monitoring something that could be noisy, we're waiting for photons, because the signal we're getting is perfectly silent, the measurement back action is deterministic. It's the same as the function of time. Okay, so how do we do this? How do we surround an atom with all these detectors and hope that they don't click? Well, we do something clever because we're experimentalists, or maybe something very simple because we're experimentalists. We just expand the state space of our system. So now we'll consider, rather than a qubit or a 2-level system, a 3-level system. And I'm going to define a new qubit as the upper manifold of states. So what those experiments look like are the following. I can prepare my system in this excited state, this F state, and I might let it evolve over time, maybe with some sort of driving or coupling between the excited state and the F state. And then at the end of a certain experimental time period, maybe a few microseconds later, I'll perform a high-fidelity single-shot readout of this Chetrite in the energy basis. That is, I do these type of measurements that Benjamin was telling us yesterday, probe a cavity, we look at the shift of the lollipops and IQ plane, et cetera. And what we can do is we can distinguish whether it's an excited state, or we might project it onto the F state. But if we project it onto the ground state, then a quantum jump has occurred. We're going to have to throw those results away. So we're going to realize the no-jump evolution by post-selecting on just the cases where the qubit is preserved through the experiment. So you can imagine that's somewhat costly. If I wait a very long time, it's pretty likely it'll decay. Will have decayed. But we have lots of time, and graduate students just continue to do the experiments over and over again, and we'll get as much statistics as we need. Great. So by post-selecting on this no-jump evolution, we get this evolution described by an effective non-Hermitian Hamiltonian. That is, the dynamics of spontaneous emission without quantum jumps. So let me give you a little more intuition to what is hiding before these quantum jumps occur. And to do that, let me first remind you what normal Rabi oscillations look like. So I've taken this system here, I've set gamma equal to 0, and so I'm just initialize the system in the F state. And I'm showing that the probability that stays in the F state goes like cosine of omega Rabi t. Pretty straightforward. Now let's turn on that dissipation. So we set gamma to something like 6 per microsecond. And look at what the Rabi oscillations look like now. They're quite different. You can see the Rabi oscillations slowly go from this excited state, the F state, to the excited state E, but then rapidly go back to this F state. So they're highly distorted. And they're distorted in some sense by the measurement back action associated with the post-selection on the no-jump evolution. Or they're distorted because they're evolving according to this non-Hermitian Hamiltonian. But intuitively, since the qubit survived our post-selection, that is, it didn't decay to the ground state, it's unlikely that it was in the excited state, which is the one that can decay to the ground state. So the fact that we have the data in our analysis block means that it's much more likely that it was this F state, which does not decay. And so that favors one state over the other. And that's sort of the magic behind non-Hermitian Hamiltonian. There's a lot of excitement, and I won't talk about it much in this talk, about sort of enhanced features according with exceptional points and non-Hermitian Hamiltonians. And the basic thing that's going on is you can see here, there's a moment where the dynamics are accelerated. Both the unitary drive from the Rabi drive and the back action are coinciding to cause the system to evolve very rapidly. So you can imagine harnessing this to generate entanglement more rapidly or to become more sensitive to small parameters that are perturbing the system, etc. Okay, so here's our system. And we'll be a little more careful now. I'm going to specify sort of two key parameters that describe the system's effective Hamiltonian. So one, there's a drive, J sigma x, that connects these two states at some detuning delta. So J and delta are the two parameters that we can use to tune our Hamiltonian. And the Hamiltonian is a simple 2x2 Hamiltonian given here, and it's obviously non-Hermitian. So what do we do once we have the Hamiltonian? Well, we write down the energy eigenvalues by calculating eigenvalues for this Hamiltonian, and they're given here as some nasty complex number. Okay, so let's plot those energy eigenvalues as a function of those two tuning parameters, that is the detuning, the frequency, and the amplitude, J, of the laser or the microwave drive that connects these states. So that's shown here. The real eigenvalues, the imaginary part of the eigenvalues versus J and delta. And they're given by these beautiful Riemann manifolds, these are sort of generic shapes associated with the square root function, that are now describe the energy landscape of our qubit. There's all sorts of cool things that'll happen as we start to perturb our system in this energy landscape. One thing that's worth mentioning is that there's a degeneracy in the system. It's a so-called exceptional point degeneracy. It's a place, well, the degeneracy of a non-Hermitian Hamiltonian where the eigenvalues and the eigenvectors become degenerate. And that occurs for some value of J and where delta is equal to 0. So many physical systems can be described by 2x2 Hamiltonians, 2x2 Hamiltonians or 2x2 dynamical matrices or whatever you like that have the properties of the previous slide. And they're broadly described as something called a PT dimer. That is parity time dimer because they have a type of parity time symmetry. So that is, if I have these two states, E and F, and if I set it up so the excited state decays at a rate gamma over 2, and the F state has gain at a rate gamma over 2. This has gain, this has loss. It has parity time symmetry in that if I apply the parity operator, I exchange the two states, E and F. I apply time reversal, I change gain to loss and loss into gain. So I end up with the same state, same system as before. What we have is something called a passive PT dimer where just one of those states has loss. And so you can equate these two by just taking out an overall identity times loss, which kind of characterizes the fact that our experiments become less and less likely of succeeding as we go longer and longer in time. Okay, so there's lots of places this shows up. There's beautiful work from Jack Harris's group at Yale studying this in optomechanics. There's work studying this with atomically trapped gases by Li Luo's group. There's a lot of work in optics and photonics. Here's some whispering gallery resonators from my colleague Lian Yang at Washington University. We've studied this in the context of parametric amplifiers, where the gain and loss correspond to squeezing and anti-squeezing of a specific mode of an electromagnetic resonator. And a lot of those share interesting similar features, which I'll tell you about now. Do you have a question, Howard? Yeah, so they're classical dynamical systems. All these systems, I mean, this is quantum, although we can describe it by a classical set of equations. And those classical systems can be described by a dynamical matrix that has the structure of the previous one. It's mathematically exactly the same as our quantum system of quantum levels, G, E, and F, evolving according to quantum Hamiltonian. So all the features one sees in these classical systems show up in the quantum case as well. There may be some exceptions having to do with, say, geometric phases and so forth. I'm not sure how specific those are to the quantum case, but the features are incredibly universal because many things can be described by dynamical matrices, and 2x2 dynamical matrices are particularly common. Great. So one of those features, perhaps the most interesting facet of these non-Hermitian systems described by a 2x2 dynamical matrix or Hamiltonian, is the notion of encircling. So remember, there's degeneracies. These are exceptional point degeneracies of that Hamiltonian. And in our system, there are two of them. And they occur where J is equal to, say, gamma over 4, and minus gamma over 4, and delta equals to 0. So you can imagine preparing our system in an eigenstate of the Hamiltonian for some choice of J and delta right here, and then slowly, adiabatically tuning the Hamiltonian parameters, so changing J and delta, and hoping that the system adiabatically follows the instantaneous eigenstates of the Hamiltonian as we go around this degeneracy. Okay, so what might happen? Well, here's those Riemann manifolds again. And so if we started off in this higher, in the eigenstate, say up here, sigma, psi minus, and we tune those parameters, we can imagine a state will adiabatically follow the instantaneous eigenenergy, so staying on the surface of the sheet, pass through the branch cut, and then end up down on the bottom, transitioning from one eigenstate to the other, even though we've adiabatically tuned the parameters, and the initial and final parameters are the same. Okay? So we've made an operation that takes us from one state to another that's completely adiabatic and occurs because of the topology of the complex energy landscape. Okay. It's kind of like one of these parking garage structures where you have the circular ramp that connects different levels, right? If you drive around the ramp clockwise, you go up a level, and if you go drive around counterclockwise, you go down a level. Okay? And it's actually pretty, even more, like it's not like there's two levels, but there's actually several levels. So imagine you started on one level here where the eigenstate's psi minus, and you drive around up to the next level, you go to the state psi plus, so you've exchanged one eigenstate for another, and you go around again, well now you're actually at minus psi minus, because there's a geometric phase you accumulate every time you go around this degeneracy. And then you go around again, you go up to minus psi plus, and so forth and so on. So it has some sort of periodic boundary conditions. So if we think about encircling in EP2, we can, so around the second order exceptional point, we can abstractly put it here as the center of some control parameter space. And we can consider different types of loops. So I've sketched for you what would happen if we go around this exceptional point, we'll pass through a branch cut, and we'll go from one eigenstate to another. One way to visualize that that's quite nice is to think about the energy eigenvalues on the complex plane. So there are two values. And when I perturb the system, well, I actually exchange the energy eigenvalues. This one goes to that one, and that one goes to that one. So you can see I've kind of switched which one is which, and you can imagine switching them one way or the other way. But of course, if I have a loop that doesn't go around the exceptional point, then I might perturb the eigenvalues, but I'm not going to exchange them. So there'll be no switch in which state it's in. Okay, so there's some sort of topological feature there. Why is it interesting? Well, it gets pretty exotic when you consider higher order exceptional points. So if we had a 3x3 matrix, then we could have a region where there's a threefold degeneracy. This is called EP3. So 3x3 matrix will have 4 independent control parameters, and there'll be some spot where there's this threefold degeneracy EP3. Okay? Yeah? Yes, so the question is, let me see if I can go to the right diagram. Why is it that I passed through the branch cut into the lower sheet rather than kink up into the, to stay on the other sheet? And I don't have a good answer for that other than that's sort of the way it's connected. This is the way I think of branch cuts. If you take a sheet of paper, you like make a cut, and the sheet of paper kind of continues through. And the branch cut's there just to sort of have some sort of representation we can have. But that's kind of the nature of passing through branch cuts, is that you stay on the right sheet. Unfortunately, I never took a class in complex analysis, so I'm really flying by the seat of my pants there. But that's the nature of it. And of course, there'll be some deviations from that specific evolution that we'll have to deal with in the talk later on. Okay. So where am I going? Well, okay, we got this idea that you can, if you go around the EP, you pass through a branch cut and you exchange the energy eigenvalues or you exchange states. We have this winding type of phenomenon. And what I want to convince you of is this gets really crazy and exotic if you have now higher order exceptional points. So around EP3, there could be 4 independent control parameters. And you could imagine that near this spot where there's a threefold degeneracy, there's actually a whole volume of control space that has a twofold degeneracy, where 2 of the eigenvalues are degenerate, but the third one is not, right? So that's shown there. So then you could imagine taking some ball, a sphere in 4 dimensions, or 3 sphere, that is a surface, 3-dimensional surface, that's a constant distance from that EP3 degeneracy. And that's going to intersect this EP2 degeneracy in specific spots. And since the 3 sphere is now a 3-dimensional object, surfaces, you could imagine plotting that in a Cartesian space so we can kind of visualize that control parameter space. So this box represents all of the spots on the surface of this sphere. And it intersects EP2 at a specific spot shown here in this kind of pink color, which happens to form a trefoil knot. And so then you could imagine different control loops now that encircle this second-order degeneracy, one that doesn't encircle the degeneracy, that's this loop here, one that encircles one of the degeneracies, and one that encircles 2 degeneracies. And those correspond to all sorts of different operations on now the 3 eigenvalues of this system. That is, if we think about this first control loop, the black loop, it doesn't exchange any of the eigenvalues. The second loop exchanges 2, but leaves the other one unperturbed, and the third braids all 3 energy eigenvalues. Okay, so just having a threefold degeneracy leads to this sort of rich physics associated with these non-abelian generators of the braid group over 3 elements. And so maybe just for the exercise of exploring the sort of mathematics of this, it would be interesting to be able to experimentally encircle these exceptional points and see some of this physics. Okay, so let's try to do that experimentally. What I'll do is I'm going to prepare my initial state, and then I define a parameter path that attunes me around the exceptional point into this other point here, where the initial and final parameters are the same. And the whole loop's going to take 1.5 microseconds, but to see what's going on in the interim, what I'll do is I'll break that evolution into successively longer chunks of time, and stop, and perform quantum state tomography to figure out what the state is doing at each point in time. So that data is shown here. So the dashed lines represent the instantaneous eigenstates of the Hamiltonian along this parameter path. And the solid lines are experimental data. Okay, so it's kind of noisy and so forth. But you can see I started in one eigenstate where expectation of sigma x is -1, and I roughly end in the other eigenstate. So we kind of see what we expect. But there are some non-idealities in that you can see there's some wiggles here. And these is from some non-adiabatic transitions, couplings between the eigenstates. That when I enter in a regime here, I actually end up coupling onto the wrong sheet at the branch cut. And now I have a mixture, a superposition of the 2 states, and we see oscillations at the energy eigenvalue difference. So we didn't quite perfectly adiabatically encircle the exceptional point. One could ask, what happens if I go counterclockwise? Or go clockwise rather than counterclockwise? Okay, so in that case, we would have expected the same thing, that I would go around here, pass through the branch cut, and end up on the lower sheet. But if you say instead, experimentally, it just gets very noisy. So why is that? Well, it's because the energy eigenvalues have both a real and imaginary component. One path, the first path I showed you, passes through a region where the imaginary component is small and negative, but it's approximately 0. So there's very little loss for this path. Another one passes through a regime where the imaginary component is large and negative, very large amounts of loss. You could say one kind of passes through the F state where there's no loss, and one passes through the E state where there's a lot of loss. And so simply in this case, there's the chance of it decaying during this process is so large that we end up with very little data left after the post-election, even though the graduate student stayed in the lab all night long. Okay, so it's kind of like in this parking garage, someone didn't build the guardrail on the side, and so when you're going one way, you have a reasonable chance of just driving off the edge and being lost. So this is actually quite a problem for the purpose of adiabatically encircling these exceptional points, because in the first case, I'm going too fast because I see these non-adiabatic couplings between the states, and in the second case, I'm going too slow because the loss has plenty of time to dominate. So what is an experimentalist to do? Well, before we do that, I point out that there are even more problems, and that there are other quantum jumps from this F state that we weren't able to eliminate with this specific trick. And so in some sense, there's, our qubit has a finite T1, if you like. And so describing this kind of breaks the nice non-Hermitian Hamiltonian picture we have. We now have to use some sort of Liouvillean description or a hybrid non-Hermitian Hamiltonian plus Lindblad description to describe what's going on. It's kind of like any kind of quantum technology. We build some sort of new type of qubit. We presume it to be a perfectly closed system, excellent and everything, but in reality, it has some decoherence rate, et cetera. And so you have to work either to reduce those decoherence rates, non-idealities, or to find ways to perform faster gates and to do the experiments before the decoherence has time to take place. So that brings us to the idea of counter-diabatic driving. Is there a way to do the experiment faster, but faster and better? That is, can I somehow transport my glass of water across the room rapidly, where it doesn't have time to evaporate in the heat, and it doesn't spill by being too clumsy? This is a well-established field in many areas of science, particularly in quantum dynamics. Okay, so the idea is we can calculate a counter-diabatic driving Hamiltonian that effectively cancels out the non-adiabatic transitions between eigenstates that we don't want. So let me take you through this story relatively quickly. So in order to explain this, we'll do the first step, which is to just try to make the control loop very fast. So before we were spending 1.5 microseconds to encircle this exception point, now we're going to do it in 200 nanoseconds. So there's the instantaneous eigenstates, as we expect to see. And when we do the experiment without any counter-diabatic driving, we see that indeed the system does not follow the instantaneous eigenstates at all. In fact, right here, when we get toward the middle of this loop, the middle of the loop, the actual trajectory is very different from the instantaneous eigenstates. One can kind of quantify this in terms of a adiabaticity criterion, which looks at, say, the overlap of my state that I'm changing with some other state that I want to minimize transitions between two. And you want this criterion to be very small if we are to have adiabatic evolution. And indeed, for this loop, here at the center of the loop, this adiabaticity criterion is 10. It's obviously not much less than 1. And indeed, we see that the states diverge from the instantaneous eigenstates of the Hamiltonian, as you might expect. Okay, so let's go ahead and now add the counter-diabatic driving. That is, if our control is to change J in this cosine pattern and delta in a sinusoidal pattern, then we can calculate the counter-diabatic term, which is this, ends up being roughly a constant drive along the y-axis of the qubit. So now, in addition to tuning the parameters, we drive it in this constant way to minimize those transitions. And when we do that, now we see the measured quantum trajectories, of the qubit in solid match the instantaneous eigenstates quite nicely. It does so for both clockwise and counterclockwise directions. And we're now able to go fast enough to avoid the sort of deleterious effects of loss, and we're able to, but we're still able to have adiabatic evolution. Yeah.
So I'm not sure I understood how you find this counter-diabatic drive. Do you minimize the criterion you showed before?
So it's a pretty straightforward calculation. So if I have my eigenstates that I'm interested in populating as a function of time, I have these two terms here that I add. So one is to sort of counteract the changes to create a drive that counteracts the way that as I change my eigenstates, it overlaps with the other eigenstate. So it's a sort of straightforward calculation.
Okay, thank you.
Okay, so we can characterize the effect of this control by looking at the trace distance between the inferred state and the instantaneous eigenstates. And when we do so, there's kind of three regimes at work. So the blue color here is where we're applying counter-diabatic driving, and the green color is where we're just doing the loop without counter-diabatic driving. And sort of the slow loops here, this is a regime where the counter-diabatic driving really has no effect because we're still going so slow that the dissipation dominates what's going on. There's a regime here where this counter-diabatic driving works in that we have a reduction in the distance between the inferred state and the instantaneous eigenstates with the addition of counter-diabatic driving. And then there's a regime here where the counter-diabatic term is simply too large for instruments to be able to apply, and so it starts to break down. Okay, one could ask, does this counter-diabatic driving preserve the topology? That is, we're interested in capturing the sort of this parking garage structure and being able to do so fast enough without driving off the parking garage altogether. So our system has these two exceptional points. So we can actually consider three types of loops. One that encircles 0 EPs, where we should map back to the same eigenstate. One that encircles one exceptional point, where we should go from one eigenstate to the other. And then one that encircles two exceptional points, where we should map back to the same eigenstate. And so I'll plot for you here the sort of expectation value of sigma x at the end of the loop as a function of j min, which passes between the case of 0 exceptional points, 1 exceptional point, and 2 exceptional points. And what you see is when we go around 0 exceptional points or 2 exceptional points, the expectation value sigma x is -1. That is, we're in the same state as we were initially. But when we pass through just 1 exceptional point, we're able to resolve the topology of these features. And it's actually quite surprising because in any kind of energetic terms or temporal terms, the bandwidth of these 2 points, they're very closely separated in energy. And so even though we're applying a control that takes place over a very short period of time, very large bandwidth, we're able to resolve the very small sort of fine spectroscopic features of this exceptional point. Okay, so I'm out of time. I'll skip my kind of summary of classical versus quantum versus non-Hermitian control, other than to say that there are certain cases, as in ours, where this counter-diabatic driving allows us to actually achieve a regime of adiabatic response in the vicinity of these exceptional points that really would not be possible otherwise. That is, we can't go slow enough because of decoherence, and we can't go any faster because of non-adiabatic transitions. Okay, so just to conclude, I told you first a story about homodyne monitoring of radiative decay as a way to introduce the concept of, the Lindblad master equation. And then we showed you how we can remove the jump term from that Lindblad master equation to achieve a non-Hermitian Hamiltonian. And then I took you sort of into the world of that non-Hermitian Hamiltonian, where now the energy eigenvalues are complex. We have this beautiful Riemann topology. It gets really exotic when you have higher order exceptional points. And finally, showing our first steps toward really being able to control quantum states in this interesting energy landscape. So, thanks for your attention.
We've had a few questions already. Let's do 3 more. I can see 3 hands up, yeah?
Thanks. 2 very short questions. The first one, when you do post-selection to get rid of the jumps, how many trajectories do you throw out of the window, 10 or 90?
It depends on the thing. So, I have 10,000 measurements, we throw away 9,000. So we throw away, out of 100, we throw away 90, so 90% of the data. It depends, though. Sometimes it's very much longer than that, but that's typically the
And the second short question, when you do counter-diabatic driving, very often you have to pay a price for that. So what's the price in your case?
So
it doesn't come for free.
It's not clear what the price is. The price may be that as we really map into the strong counter-diabatic driving regime, we can actually turns into more of like a gate-based architecture. That is, the driving starts to look like a very strong gate around this thing. The driving term actually is much larger than the non-Hermitian Hamiltonian by any terms. And so are we really evolving according to this non-Hermitian Hamiltonian? Or are we just devising a sequence of gates and driving that captures a trajectory that has the same features? That may be the disadvantage. Thanks.
Abhishek?
Hello. Yeah, so I have a question regarding your first few slides, this quantum state diffusion like experiment that you showed. Can you just?
Can I go to them?
Yeah.
100 slides ago? Sure.
Yeah. Yeah. No, sorry. Yeah, the block sphere like.
Yeah, of course.
Yeah. So I mean, when you're plotting something of block sphere, it's some expectation value of sigma x, sigma y, sigma z.
Yes.
But so you have one diffusion, like state diffusion trajectory. Then, like, what are you averaging over experimentally? Yeah.
So, okay, a couple interesting comments. For one, because we're doing homodyne monitoring, our measurement is only proportional to the expectation of sigma x. And so in that case, our dynamics are confined to the xz plane. So I'm not really throwing away stuff about the y direction, which is actually beautifully seen in Benjamin's group work, where he's sensitive to both sigma x and sigma y. So what I'm just throwing away, or what's going on, is my signal here is contaminated by noise that's replaced the original quantum signal. And so I have to average over undetected homodyne signals, which would in principle have also given me information about sigma x. Or you could say the undetected signal could correspond to quantum jump evolution detected by someone else, or it could correspond to measurements of a different quadrature, that is measurements of sigma x, of sigma y, and so I have to average over those in different ways. And in fact, there's a lot of work to sort of, if I want to infer a pure state trajectory, how do I unravel those undetected events, and what does that mean in terms of the ensemble of trajectories underlying each of these sort of average trajectories?
No, but in the experiment, so you get this signal, and then what do you do? Like how are you getting those black lines on this?
So I get the signal, and each signal here I actually plug it into a stochastic master equation,
Okay.
as shown previously, and I have added these stochastic terms. Each one carries a measurement record R with some efficiency eta.
Okay, thank you.
Hello. Thanks for the talk. I am very much interested in the using of this counter-diabetic drive to speed up through the decoherence process, as you showed there. But so certain decoherence are not uniform throughout the block sphere. There are regions where effect of decoherence is more. Can we optimally control the counter-diabetic drive to speed up through those regions even faster, and would it give you even better result?
Yeah, so great question. So that's indeed the case here, that regions of our block sphere are much more lossy than others. That is, the excited state is much more lossy than the F state. And so initially we thought maybe we can just accelerate through that region as fast as possible. But indeed, that's actually a region where now the non-adiabatic transitions are the worst. And so we could certainly build a control that tries to go through that region faster, but then it will require an even stronger counter-diabetic driving term. And so there's always going to be a trade-off between how fast we can go and how fast of a driving we can do to counteract those transitions. So certainly we can choose loops that
Thanks.
optimize over avoiding the lossy regions.
Thanks.
And let's thank Keita again and all the speakers of the morning session.